Okay.
Got it.
Ready to go.
Okay, so day 2 of module 2 of the grad course Tame Phenomena over the Real Field. I want to just repeat that we have these informal resource pages that some of us have put together. You can access one for the main program here. It's Google Sites thingy, and you can either go for this particular module, what I'm doing. You can either go directly to here. I know that's a long URL, so I'll leave it up for a second. Or it's also accessible from here. And again, what's on these things, more or less? Well, first of all, any instructor, any lecturer for any of the grad courses stuff is sort of welcome to contact, I guess, me or Philip. And if you want to post any extra material, we can just put it here. The advantage of this is that we don't have to go through fields. We're just running this ourselves, and so it's fast and loose. And so that's a good place for this. And again, some of the things that I'm putting on my resource page in particular are versions one way or another of papers that some of which were published in conference proceedings and still have never been made available online, except by the authors on their web pages or something. So some of the references or that I might cite, or some other people might cite, you're not going to be able to find them online anywhere. And let's face it, we don't really have the option to go over to the UT library maybe and start digging through the stacks to find some ASL conference proceedings from who knows when. So that's kind of what these guys are all about. It's just a place for us to put stuff to make it convenient. So, and let me also just remind everybody here that I was told that this is a graduate course, so that's the way I'm approaching it. I really would prefer that everyone else look at it that way as well, and not as simply an excuse for senior people to discuss things with each other. So I want grad students in particular to, yes, there's these scheduled question sessions that might come up, but as with any graduate course, I'm potentially available for discussions by appointment. Okay, so I think now I need to switch to stop this and start this. Okay, hopefully everybody's just seeing a blackboard, an electronic blackboard, more or less.
Yeah, it's fine.
Okay, great. And yeah, I do need to hide these, I guess. Okay. All right, so where we were on Monday, yes. So I tried to convince you basically that one of the things we want to do is that when we want to start looking in this program for expanding things by trajectories of definable vector fields, that we really ought to at least be assuming that the vector fields come from an L-minimal structure. And the reason for that was that most of the time, the vector fields we're going to be looking at are, well, they'll at least, continuous things on constructible sets. Constructible, recall, just means Boolean combination of open sets. And so the graph, continuous, actually constructible functions on constructible sets are, of course, constructible when they're regarded as their graphs. So most of the time, if we're expanding by vector fields, or we're looking at constructible vector fields. So if you recall that I had this, if I have an expansion of the field of reals by constructible sets and it's not O-minimal, I gave some indication as to how to define what I was calling a sloppy sine function And then from here, from the existence of that, it's very easy to concoct loads and loads and loads of absolutely ridiculous vector fields that no one would ever really want to classify or be interested in. So as part of that, I wanted to talk a little bit more about part of that, because as part of the proof, I was thinking I should give people a chance to play around a little bit with these. If you haven't done these kinds of arguments before, it's good to get some practice maybe. So we'll just start off with something here. This is going to be toward a little exercise. So let E and R be infinite and discrete. And remember, discrete here just means that every point is isolated in the set. And the claim here is that from here, now remember, R bar just denotes the field of reals as a structure, and I'll generate the structure over it by E. I'm going to claim that I can goose this up a little bit to get something better. Defines, let's say, an infinite, I guess I'll say uniformly discrete, why not? Subset of R. Now, what do I mean by that? I mean that all of the points are separated by at least some, they're all separated by some distance. So that is, so there exists some C such that, oh, I guess I better give it a name. There exists a C such that, say, for all X, Y, and D, if X is not equal to Y, then X minus Y is greater than or equal to C. And this should be bigger than 0. So that's what I mean by uniformly discrete. Another way to look at this actually is just to say that, say, for all X and D, the distance function between X and D minus X is greater than or equal to C. Okay, so now you say, well, that's pretty, I mean, it's obvious to go from an infinite discrete set to some of these other things. But now remember, the set of midpoints of the complementary intervals of the Cantor set, there's an infinite discrete set. And it is not, I don't know that it's patently obvious how you get from that to one of these other things that's unbounded and lots of other things. So what this is really going to be left is it's an exercise, if you will, but I'm going to give some hints. And so basically first of all, we would see that if we look at something like this, whoops, I still prefer undoing with an erased chalk eraser, but that's not going to fly today. So X in E and distance of X here is greater than or equal to R. Well, first of all, this is definable. And that's just predicate logic, really, because E is definable. Oh, hang on. Somebody's off the reservation here. Okay. There we go. All right. Right, that's just because E is definable and the distance function is definable and all these other things. Okay, so we've got, so that's something to keep in mind if when you're playing with this a little bit. And then there's a trivial case distinction that we can make here. So either, here's the case, there exists an R greater than 0, well, such that one of these is infinite. well, then we're done, because we've actually just, then the set, this set itself is certainly going to be uniformly discrete, because that's the, if you've got an R that works, then you're done. So the case is, what happens if it's not, if you don't have one offhand that's infinite? And so what happens then is, if otherwise, well, they're all finite. All of these guys, which you can think of as you like as fibers of this thing, all are finite, hence either empty or max exists. Right? And so you can go through here. Now, we know that we know that we're starting with an infinite discrete set here. So at least from some point on, we're not going to have to worry about, from some point on, these are going to be non-empty, or actually from some point on, as R gets smaller, these guys get bigger. So I shouldn't say it that way. As R goes down to 0, these will not be empty. And the maximum always exists. So now you can start drawing some little pictures about what happens with that maximum function as you go down, as R goes down to 0. And you see there have to be little jumps at times, and those jumps, so you, yeah, okay, you have to look at the picture of what happens with the jumps. That's my hint for this. Any questions on any of this stuff so far?
Yeah, just a.
I have a question, Chris. So some of these D's are E's, I think, right? Last capital 2 D's are actually E's, right?
Oh, some of the, let's see, wait a minute. So this is, oh, this should be E, is that? Yeah, oh yeah, because I'm trying to find.
We are trying to find D.
Yes, we're trying to find D.
Yeah.
I think I had these reversed in an earlier version or something. Thanks, Ihan.
Yeah.
Something else?
No.
Okay, so I'll just leave that as something to play around with. If you get stuck in the end, there's a you can ask if you get stuck in the end, ask me and I'll tell you which paper to go look at, or something along those lines. Okay, so now let's get back to where we were. It's really important. It's really important to get your hands dirty with these kinds of arguments. It's great to sit around that we have these definitions of structures that we can give to non-logicians very, very easily in a couple of minutes and not have to explain any logic. But if you've ever tried to work with this set theoretic definition of structure, if you will, it's very unwieldy until you learn how to translate these operations into first order logic and start to think that way. So this is a good opportunity to develop some skills if you haven't already done these kinds of things before. All right, now, so we'll eventually come back later to this idea of when we start doing actually more with ODE theory, we'll eventually come back to this contention of mine that you get horrible vector fields that no one would want to look at. But there was another side to this that I didn't get around to talking about. And of course, you could say, well, maybe if you have an expansion of the field of reals by constructible sets and it's not O-minimal, well, then maybe you just define the integers outright, in which case, I guess the whole program's kind of over. Now, that's not an unreasonable question, but as luck would have it, no, there are examples. There are examples of expansions of the field of reals by constructible sets that are neither O-minimal nor define the integers. And we're going to talk a little bit about those right now, some of them, because they play, they're going to play a very important role in what follows from here. So let's see. let alpha be a, and we're going to consider, look at this, this notation I'm declaring here. This is going to be the cyclic group generated by this guy. And of course, it could be one, in which case that's not very interesting. But so this is just some notation we're going to be using. Now, in something, it had a really big influence on me early on in my graduate career is when there's a paper by Vanendries that where he actually shows that that if we, okay, maybe I'm gonna have to cheat a little bit on when we talk about languages or whatever. Well, maybe I won't. I just won't talk about it. If we look at this structure here, we take just the real field and throw one of these guys on there. This is obviously not O-minimal, obviously, because this thing has infinitely many connected components, but it does not define the integers. So here we have an example, right? I mean, this is a locally closed set. It's intersection of an open set and a closed set, so it's certainly constructible. All discrete sets are constructible. But it doesn't define the integers. In fact, there's a lot more to the story here. Indeed, if, let me see if I remember. So if alpha is algebraic, then the theory of this thing is decidable. In the sense of classical logic. And even more generally, if you weren't algebraic, then you would simply say that the theory of this is decidable relative to an oracle for the cut that alpha makes inside the rationals or something. So this is a very influential paper on me at the time, and I still like all this very much. So here we have examples. This is one of the first one I ever saw of where you have something, an expansion of the field of reals by topologically pretty nice object, and all hell doesn't break loose. Now, I actually, at some point, a far more senior model theorist than I told me that a lot of people were really surprised by this, that they sort of had expected that as soon as you throw an infinite closed discrete set in somewhere, order type omega kind of thing, then you really should have a problem. But this is also, I should say, it's axiomatized in sort of the most obvious way, reasonably obvious way. So this is a good example of something. And in fact, we can gin this up quite a bit by generalizing the proof that Vanendries gave in later on with more tools. This actually, so if we get a whole class of these guys. So if R is, remember, this usually just denotes just some expansion of the real field. If R is O-minimal and defines, well, I'll just say it this way, and defines no irrational power functions. If I have to, I can say what that means if necessary. Then this guy actually is pretty nice. I mean, it does not, in particular, it does not define the integers, but actually there's a whole lot more is true. In fact, what happens here, we have a very, very good description of the definable sets in here relative to those in here. And with this group acting on them in a way. And I don't want to get bogged down in making that precise at the moment, but these are very nice structures, actually. I mean, in fact, you can arguably they're as nice as you could be for defining an infinite discrete set. I mean, I can say one property that they have is that every definable set in one variable either has interior or is just a finite union of discrete sets. So you can think about this as a natural sort of first step beyond minimality, which you can rephrase as every definable unary set either has interior or is finite. So we just loosen that to or is a finite union of discrete sets, and these have this property. Now, these are going to play a really key role also in everything we do. This is, yes, okay. These are going to be important, and I think they deserve more attention than they've been getting over the last few years. Okay, so we've got some important examples here. We've started with this. We now see that anytime we have some people, by the way, for those of you who might know what this means by no irrational power functions, that's the same as saying that you have field of exponents, the rationals. Now, when I say define a power function, that means the whole thing, like all the way out to infinity, or equivalently all the way down to zero. Compact pieces of these guys, that's fine. You can define compact chunks of your rational power functions, should say logarithmically compact or something. But you can't have irrational power growth rate here. And we'll see why. Well, you could say, first of all, because the proof required that you don't have this. The proof of this actually, it's model theoretic. The only proof I know is highly model theoretic, relies on a saturated embedding test and the so-called Wilke inequality, which was a result of Lau generalizing something that Alex Wilke did in his proof of the model completeness of the reals with exponentiation. So I don't know a standard proof of this, by the way, and we'll get back to that again later too. Okay, so great. We have some non-trivial examples of things to look at, but we also have a severe, we still have some overhead on us. And let me get to that next, because this is something we have to keep in mind. All right, whatever that was. So a special case of a theorem of Philip, neuronomy. So again, just a special case, but this is the one we're interested in. This was 2009 when it was actually done. I don't know when it appeared, but the important thing is that this was done at Fields in a 6-month program, similar to what we're doing now. Philip came in as a postdoc and produced this result. So once again, showing that Fields has been really important in the development of the subject. So I'm going to state it this way. Let's say if alpha and beta are greater than, well, we'll just say 1 for the heck of it. And log alpha, log beta are Q linearly independent. And all right, Q independent, forget that. Then we get the integers. Hence, game is over again. And this question was raised all the way back in Lau's original paper on this, with just alpha equal, I think you could, if alpha is 2 and beta is 3. So basically what we've got here is that this says that, yeah, it's fine. I can start with one of these O minimal things that defines no irrational power functions, and I can add one of these things. And of course, as long as I've added one of them, I also get all of their rational power images. So those are automatically there, but I can't add anything beyond that without defining the integers. So I should, by the way, what do I mean? So this is a set, right? So if I look at the image of it under, well, actually under any real power, if we go back to the definition of this and write it out, this is just going to be the number alpha r. It's the group, this group here. So these go back and forth. And since I'm over the field, all rational powers are definable. So as soon as I have this guy, I have all of the alpha to the q z's. So, but when I start talking, if I start saying things like defines exactly one alpha z or something, it means modulo rational power images. So, so this puts a lot of, remember, once we define the integers, we give up, or at least we say, well, we know we can give up because we can't play this game in terms of definability. All real projective sets are now definable, and that's descriptive set theory. So we have to move on from there. So with this result, I wanted to get these examples out right away. But if we sort of put this together, we come up with a little trichotomy theorem. Or we'll just call it a trichotomy. For the moment, that's all I'm going to say. So remember, one of the following is true, and it'll be exactly. So remember, my structure R here defines no alpha z, well, with alpha not equal 1. It'll always define that one. R defines exactly 1 alpha z. And by here, what I mean by that is, again, up to rational power images. And finally, R defines the integers. So what this tells us right here is that if in order to remain, and you recall, hopefully from the first lecture, I said where we really want to rule these out. We don't want, to be doing this kind of stuff. So we kind of like to say, we don't want that. So if we're looking for tameness, then our choices are that we're dealing either with something that has no non-trivial cyclic multiplicative subgroups definable, or that, again, exactly 1 up to rational power images is there. These are the only choices we have for tame behavior in expansions of the field of reals. Do we have examples? Well, we certainly do, because this would be true for every O minimal structure. All O minimal structures certainly don't define any of these multiplicative groups. On the other hand, we also have a bunch of examples that I just mentioned. Namely, if we started with, if R happened to be the expansion of an O minimal structure with field of exponents Q by one of these groups, then that's an example here. So let's reflect on this a little bit. Now, I haven't mentioned anything about vector fields or control theory or anything for a while. This is just this is either good or bad news, depending on the way you want to look at it. But this really does constrict the search for tameness over the field of reals to these two cases. And these are going to be very special, actually. There's really not too many of them around, but there are some that matter a lot. And on the other hand, there's a lot of these guys. If all we say is that R defines no cyclic multiplicative groups like this, yeah, we now know of lots of examples of these things, but a lot of them are kind of goofy and have absolutely nothing to do with solutions of differential equations, at least as far as we know. So running in the background of what we're going to be doing is this trichotomy and breaking down that we don't really have a whole lot of room if we're going to be investigating tameness over the field of reals. I keep emphasizing that field because at some point later on, I'm sure Philip will probably say something about this, but this is one of the reasons why it actually makes sense to start looking at tameness over the ordered group of real numbers, rather than just saying, well, I'm not interested in anything but the field. I understand that feeling quite well, but actually we will get pushed at some point into seeing what happens. Multiplication is the source of the trouble in all of these things, not addition. Okay, questions? Okay, I think that I think what I wanted to do at this point was jump back to some of the slides from the introductory talk and recap some of those before we keep going. So let's do this, I think. And then we'll do this. Oh. All right. We should be seeing slides now. All right, yes, so let's just, yes. Okay, good. So let's just remind ourselves here, because there's so much variation in the literature on these definitions. To me, until I say otherwise, a vector field is just a map from some subset of Rn into Rn. A solution of F is a differentiable thing on some kind of interval that's not a point, so that we satisfy this differential equation. And to me, a trajectory is going to be the image of a solution. All right, now let's surprise myself and see what I've got next. Yes, okay. So we're going to need we want some notation now. And so I'm going to let little omega generally range over non-zero real numbers. I suppose we could make it 0, but that would be annoying. So here's a vector field depending on little omega. It's a nice planar linear vector field. We surely would have seen this in a good undergrad course on ODE theory at some point, but who knows if we remember. And I think what explains everything about the behavior of this thing is really that this is, if you go to complex coordinates, this is just left multiplication by 1 plus I omega. So that I always find that helpful to keep in mind. And we're going to let m omega be this guy here, which in retrospect, I suppose I could say that this is, let's try something. Let me see if something's going to work here. And all right. I'm just sorry, please excuse me. I'm trying to see if this is going to work now. Oh, it's in red. Oh, well, okay. this is alpha Z with, oops, alpha equal E. Oh, this is very weird. Okay, so the M omega is an alpha Z. That's the point. Yeah, this looks right. So now I need to end this annotate or something, don't I? Yeah, I do. So one of the reasons why I'm using this this strange Blackboard product that I'm using is because I still can't quite figure out what the Zoom whiteboard does, why, when. I haven't figured out the algorithm yet, especially when you're on a Linux machine. Okay, so these are going to be some groups. This is going to be some vector fields. These are going to be really important. Oh, now what do I do? How do I get rid of this now? Right. There we go. Okay. So what we're going to do now is take this trichotomy that's an easy corollary of this special case of Phillips result and retool this a little bit for our own use here. So I'm just going to call it the main classification. And remember, we've got our designated R somewhere. So exactly one of the following holds for R. No M omega is definable, right? So that's, again, none of these guys. So that's the same thing as saying that you don't define any non-trivial cyclic multiplicative subgroups of the positive reals. Same thing. Now, it could be that one of these things is definable, but then no non-trivial trajectories of any of these guys are there. Strange statement, but okay, there you are. By non-trivial, I mean a trivial trajectory is just a point. So if you're non-trivial, you're more than a point, and because you're a trajectory, you have to be connected, and so now you're something big. It could also be that for some omega, all trajectories of these guys are definable. For the I'm only putting in non-zero here because the notation doesn't make sense for q equals 0. But no unbounded trajectories of any f tau with tau not a rational power, a rational translate of omega. And then the fourth possibility is R defines all trajectories. Now, this one is because, so let's, how is this coming from this trichotomy that we were looking at earlier? Again, this is the case that there are no cyclic groups. This is the case that you define more than one. That's more than one strictly different ones. You define the integers. That's the same as saying you define all trajectories of all vector fields, because according to my definition, trajectories are necessarily F sigma sets. Hence, they're certainly Borel. Hence, these are all definable in the expansion of the real field by the set of integers. Now, here's where things are different a little bit, because the case, so this is where the case where we have exactly one, if you will, one of these groups show up, it splits into two cases. And the one we're interested in is really going to be this one. This one is basically saying that there's an M omega, M sub omega is there, but really no non-trivial trajectories of any of these associated vector fields are there. So no arcs of anything are there. Just this group is sitting there by itself. This is it happens, but it's in all the cases we know of. Let's be careful how I say this. You can change this case into this case by just adding the trajectories that are missing. But whether that's always true seems to bump up against some transcendental number theory. So we're not going to be able to solve that. Now, again, let me reiterate, this theorem holds for any expansion of the reals whatsoever. So hopefully I already managed to convince us that if in our quest for expanding things by trajectories of definable vector fields, we've hopefully convinced ourselves that the base structure, if you will, in that should be O-minimal. And on the other hand, we wanted to wind up on the other end after making these expansions. We hoped to not get this case. We wanted to avoid defining the integers. So the way this is resolving now is that we start with an O-minimal expansion of the field of reals. We expand by trajectories of definable vector fields. We certainly want to avoid defining Z, or at least identify when we're going to define the integers, because those trajectories contain too much information. And the only case, and ideally, we basically are going to wind up in this case. So starting with O-minimal, we hope that we wind up in this case, but maybe we have to add a few extra bounded trajectories. We might have to add some compact pieces that we're missing somewhere along the line. But my contention is that in the end, if we're trying to do tameness of control theory, any kind of tame differential geometric control theory, and we're trying to do it beyond O-minimality, it has to be in here. It has to be in this case. So again, whether you want to look at that as good news or bad news, it's good in the sense that there's no wildness of no crazy lattice of further cases that we have to look at. But on the other hand, this is the only one left. And so structures that satisfy this, again, would have to be investigated carefully if you wanted to have if you really wanted to be looking into tame control theory beyond O-minimality. If you're working over the field of reals, Questions on anything? Okay, now I know there was a bit of a jump in taking saying, well, this was the former case that we define exactly one alpha Z basically, and it splits into these two cases. And in order to, I think we really need to see some examples in order to understand what's really going on there. So let's take a look at some of these guys here. Well, the field itself certainly defines no M omega because the definable sets in the field of reals are the semi-algebraic sets, and for darn sure, semi-algebraic sets have finitely many connected components. So this is an example of the first one. Now, as already mentioned, by Van Andries, Okay, with a little work beyond there maybe, but we can start with the field. We can add one of these M omega guys, and then we can then actually prove that this defines no non-trivial trajectories of any f taus whatsoever. And in fact, what you get here is that every definable set in the expansion of this guy is a countable union of semi-algebraic sets. And you certainly can't, and you can't get the other trajectories of these guys are arcs of logarithmic spirals, more or less. These are transcendental objects, and so you could not define even compact arcs of them. No compact arc of any of these things can be a countable union of semi-algebraic sets by analytic continuation. So there's an example where we do have one of these things and nothing else. No other trajectories of the vector field, no trajectories of the vector field. Okay, so now we could do the same thing though. Now we'll just take the expansion of R by all trajectories of these guys. This defines no unbounded trajectories of any f taus with tau not a rational multiple of the omega that I started with. So this shows how we can, and this was an example of one of these things where we have a group, but really none of the trajectories that are associated to it. But if we just add them all, then we actually still get a very nice structure. And in particular, we don't define the integers. Because, well, if we're not defining any unbounded trajectories, that would be a bunch of F sigma sets that we are not able to define, and so we can't get the integers either. So now I guess we should finally get around to doing doing a little bit of basic vector field theory. So here's my little exercise here, and we'll talk about this. I'll try to give some hints, but I'm not going to do the whole thing. You should think about this. So let's start off with a non-trivial trajectory of one of these F omegas. And remember, this is really just this is just really just complex multiplication by 1 plus I omega. Again, this explains everything. Then this structure, if I take the field, and then I add this M omega and this non-trivial trajectory, then this defines all trajectories of the F sub Q omega for non-zero rational numbers. Now, so how do we go about doing something like this? Now, one of the things that I've been sort of hiding under the table here is that there's a particular trajectory of the F sub omega that we care about quite a bit. And that's the logarithmic spiral that's associated to omega. So let's see, I'm going to try this again. It kind of worked before. Let's try this. So let's look, there's a particular, wait a minute, did it do anything? Maybe I can change this color. I don't like red. Oh well, forget it. E. I keep wanting to write this in complex coordinates. I think, is it, well, wait a minute. So let's just maybe draw a famous picture first. So logarithmic spirals, we would have run into in undergraduate courses, and they come in this way and they come out this way. I know that's a little sloppy looking, but that's the point. And the omegas that it has to do with the rate at which they twist. But we would have learned various hopefully various cool things about these guys in undergraduate math. Like, for example, that if you cut off at any spot and go ahead and follow it into the origin, you'll have a finite length that has finite length, whereas that won't be true of a lot of other kinds of spirals. So if thinking about this from a complex point of view, it's pretty easy to see that there's a particular log spiral that is associated, that is a trajectory of f sub omega, and it's then a multiplicative subgroup of the non-zero complex numbers. I mean, if we are on here, if we're on one of these guys and we take a point and we multiply it by another point on here, we're dilating or expanding or dilating and rotating at the same time, and this is a subgroup. So, and what you can get from just the ODE theory involved here is that the trajectories, the maximal trajectories of the f sub omega are really just rotations of the log spiral by a complex scalar. And from there, you should be able to unpack the rest of the exercise. Again, I'm trying not to just sell the farm here or anything, but these are interdefinable, right? So this guy here is actually the same as the expansion of the field of reals by all trajectories of the FQ omega. Oh yeah, so where does the M omega come from? Well, that's the intersection of the log spiral with the positive real line. That's where these come from. So if you already know how to do this stuff, that's great. If you don't, if this looks unfamiliar or you feel rusty or you haven't done it, you really need to work through this to figure out how this works. It's absolutely critical to understand this. So I will leave that as an exercise. Let's see, now I gotta get rid of these guys somehow and then get rid of this. All right. So here's, I mentioned these in the introductory talk. We're getting away from just little exercises now and into some things that are important. But evidently, if I'm starting with a no minimal structure, then none of these groups are there except, oh yeah, that's right, no M omega are there. Because remember, well, omega is not zero. So this is a restatement now of what I had mentioned earlier, that if R is O-minimal and defines no irrational powers, then this guy defines no unbounded trajectories of any f tau with tau not in here. And the point there is that we know you can't, there's two ways to look at this. You can, no, we'll say maybe, I don't know, two ways to look at it. The point is that through model theoretic methods, we have a very good description of the definable sets in here relative to the definable sets in the downstairs O-minimal structure. And I will get around to making that precise later, but again, it's still for those in the know, there's a very strong form of relative model completeness holds, but even that is a little hard to deal with. But in an appropriate language, we have QE and universal axiomatization, and that allows us to really start cranking out a lot of information about these things. But now it's not quite yet the time to be beaten on that. I actually hope to prove one of my, on my wish list for this, I think it would be really fun if some enterprising graduate student or postdoc or somebody could come up with a standard proof of a bunch of stuff that I'll tell you later. A standard proof that gives the descriptions of the definable sets here. Okay, so this is a fact that is not an exercise, and that's for sure. And I'll try to outline how this works more later. And here's another one that is also much more than an exercise. That if we start with a no minimal structure, then we can always expand R by all compact trajectories of linear planar vector fields. Now, again, compact trajectory here, it just means that it's a trajectory and it's compact. Remember, I don't require trajectories to be maximal or this or half maximal or anything else. They're just images of solutions, and solutions don't have to be anything either. Oh yeah, linear means homogeneous linear. So what's good about this is that we can always, what's good about this is that if we're back in one of these situations where, remember I mentioned something that like occasionally we might have to add some trajectories that we missed or that weren't there before or something, this is related to what I was saying there. Now, but why is this true? This is a very, very special case of the so-called Pfaffian closure technology, which is a big theorem due to Patrick eventually. In fact, we can also say a lot more here, but this is good for now. Essentially, all you need to know here, in order to get all compact trajectories of linear vector fields, all you really need is the restriction of complex exponentiation to a rectangle, a non-trivial rectangle. And then you can use the fundamental theorem of linear vector fields to, well, actually crank out not just all the trajectories, but even all the solutions will be there. All right. And we want to remind ourselves of this. So in contrast to the cheery statement that we can always expand by compact trajectories and know something here, if R is O minimal and it has field of exponents Q, say, is the same true of the expansion of R by all compact trajectories of linear planar vector fields. What's the difference? We know that we know that O minimality will be preserved here. But we do not know whether all of a sudden you can start defining global irrational power functions. We simply do not know this. For that matter, we don't know that you can't define exponentiation itself. Maybe if your downstairs O minimal structures is really weird and hides a lot of strange second order information somehow. I mean, we just don't know. So and again, there seem to be connections to transcendental number theory, unsolved problems, of course, in transcendental number theory. So this is an area where we're going to tend to want to axiomatize it away, if you will, so that we don't have to face up to this. Yeah, this has really been annoying for many, many years now that we don't know the answer to this. Okay, so, oh, excuse me just a second. Oh, actually, sorry. We will take a 5-minute break. 5 minutes.
Sure.
Back in 5 minutes.
Okay, you can go ahead.
Okay, all right, great. So putting this stuff together, and I really want to lay out my case carefully before we start, just, getting into details and things. I now want to contend that remember the game now is starting with, we're starting with a base structure here, and we're going to want to expand this by trajectories of definable vector fields. The vector fields are definable in here. The trajectories might or might not be. Of course, if they're already definable, that's great, but we don't always know. So that's a sub game. But we should play this game only over structures that, so we want R to be O-minimal. I hope, that was the argument about the sloppy sine function and coming up with ridiculous vector fields. I also want to say that this defines no irrational power functions, so field of exponents Q, and defines all compact trajectories of linear planar vector fields. And we could require more, by the way, but at least this stuff. So let's go back over and say, why shouldn't we have any irrational power functions around? The reason for that is let's look at this from two ways. Casually ask a professional ODE theorist if they really care about any vector fields that necessarily need irrational power function growth at the origin or something. You're generally going to, you might get a funny look or something, but people generally know they don't come up. That's one way to look at it. We're looking at it from a different way. Having an irrational power function means that as soon as I try to add a logarithmic spiral, I'm doomed, because we'd get an irrational power, and then we'd get two multiplicative groups. We'd be by Hieronymus theorem, we'd already be defining the integers. And we've said we want to figure out how to avoid defining the integers after we've expanded by trajectories. So there's two different ways to see this argument. It's like, well, they don't come up and they're unnatural or they're weird. And the other point of view is that as soon as some of the trajectories that I most want to add are these logarithmic things, these spirals, and then the game would be over, we'd be toasted. So that takes care of this assertion. And as for defines the all compact trajectories of linear vector fields, remember we can always add all the compact trajectories and preserve omnimality. But now remember, I just said we don't want to have any irrational power functions. And recall that we don't know if you can keep that property when you expand by the compact trajectories. So this is the realization of what I said about we're going to have to sort of axiomatize away these possibly really deep problems in analytic number theory by just saying, okay, fine, our O-minimal structure already has to be this nice. No irrational power functions, all of the compact trajectories of linear vector fields, and you have to be O-minimal. And then, of course, these are the vector fields we should start with, and then we hope, and then if we're going to avoid, if we successfully avoid defining the integers, then really we have to just be in a situation where essentially we added log spirals somewhere along the way. So and we know, and we pretty much do know, the model theory of those things. So our path is fairly well charted for us. And the question is whether we're willing to slog through that or not. But let's look at a prototypical example that we've seen that's come up before here. R is R sub n, which is the structure consisting of all globally sub-analytic sets. That's the, let's see, I guess this is basically the same as saying you have the expansion of the field of reals by all compact real analytic submanifolds. I think that's the same thing. Anyway, so any way you like to look at it, or these restricted analytic functions, which is the model theoretic way to talk about them. But here's a prototypical example. It's minimal. It defines no irrational power functions. That was something pointed out by Van Andries early on in the game. There's the definable functions there of one variable have these Puiseux expansions at infinity. And so you have to have rational power growth at infinity. And as for the compact trajectories of linear vector fields, well, yeah, it defines all compact trajectories of analytic vector fields. Because if you have a real analytic vector field and you have a compact trajectory, then that's going to be that's going to be real analytic as well, a real analytic submanifold. So in this case, not only do we just have all the compact trajectories of the linear planar vector fields, but we have all compact trajectories of analytic vector fields in any number of variables. So now the thing is, what trajectories should we look at? Because that's another thing we have to decide before we go. Now, so at the moment, I'm going to contend that we should only consider, at least at first, only trajectories of definable vector fields that are also locally trajectories. And what I mean by that is that anywhere I look on the trajectory, I didn't say it's closure. Anywhere I look at a point on the trajectory, I should be able to find a small ball around there where, once again, I am a trajectory. So what this, I mean, we can, here's you know, here it is written out in logical form. And what could go wrong? You could have some wobbling of your trajectory going on. And if you, at a bad point, if you pick a bad ball, you might cut it up so that now you've got several trajectories living in there. So it would be a union of trajectories, but not a trajectory anymore. So this property of, I don't know that this property has a name. It's actually it's what it's like being like locally path connected, except you have to be locally, except the paths have to be solutions of the vector field that you started with. It's maybe not exactly the same, but it's pretty close. Now, maybe one of the reasons why, because if you draw a picture of what this means, if your trajectory happened to be a C1 submanifold also, then that would take care of that. So what happens often in ODE theory is that this property isn't stated first. It's sort of overwhelmed, if you will, by assumptions made on the vector fields. Let's say that they're C1 or C2, or that they're non-singular, or lots of things. So normally, these are the things that get looked at anyway. But for me, I wanted to try to single out a definition that didn't depend on having to put restrictions on the vector fields first. This might not be the be all end all of things, but we'll start with this now. So I'm going to have to call it something. So why not call it regular? Haha. In fact, again, if you were dealing with sufficiently smooth things, your trajectory, this would just be saying that regular would mean regular as in the case of C1 smooth point. And now, so in order to keep all this in mind here, we need to look at these anti-examples of what we don't want to look at, and maybe have to, we might have to defend someday why we're going to do this. So I like this one a lot here. Cosine t, sine t, cosine square root of 2t, sine square root of 2t. This set, let me explain a little bit the notation I'm using. This is a trajectory of this thing, which is really f1, f sub 1 concatenated with f sub square root of 2. So this is a vector field going from R4 to R4, where just the first two components are this and the second two are given by this. Now, it's not hard to check that if you look at this whole thing, it's dense and codense in the Cartesian product of the circle. This is not what we have in mind for this is not what we have in mind for the kind of things we want to keep an eye on. I mean, the problem with this is that, say I'm at a point on this trajectory and I want to sit around and control what happens near that point. That is not going to happen here, because no matter what neighborhood I draw around there are going to be things leaving and exiting and doing all kinds of crazy stuff. And if you on my resource page, by the way, I point out that Perko's ODE book is a good source for basic stuff. And it's, if you have access to Springer Link, you can download the whole thing for free. In books like that, these might be mentioned somewhere, but they're never regarded as very serious. This is some people would call this an abstract center, I think. They're more to be regarded as ergodic theory, maybe, than anything else. I mean, of course, if you take any compact trajectory, a compact connected subset of this, then you're going to be definable in R sub n, because this is certainly an analytic vector field. And so all the compact trajectories of that vector field are definable in R sub n. The problem is if you allow the whole thing, you wind up with this, as I said, it's sort of ergodic, filling everything up under the action, which kind of makes it a different subject. So I think you don't see things like this talked about very much in books on control theory. Now, more interesting actually are things like, if you've heard about these guys, I was tempted to go look up the pictures of these on the internets and all that, but then I'd probably have to be careful to credit them properly. If we look at these things, so-called strange attractors are also things that show up in dynamical systems. And we've probably all heard at least the phrase strange attractor. Here, it's not really ergodic anymore. If you take a non-periodic trajectory of these guys, say you wind up, you have chaotic behavior. So you're not exactly sure when something returns and when it doesn't under small perturbations. So this belongs, these kinds of things, fractals, if you will, belong more under the wings of catastrophe theory or something like that. So, and by the way, these certainly are not constructible. When this is certainly not a constructible set, it cannot be a Boolean combination of open sets. That's something else you could check. Similarly, now these guys can be constructible, but if they have like cross sections that look like Cantor sets or oddball stuff like that, so we're not going to be looking at these guys either. They are not what I was calling regular. It's not the case that you can go to a point and stay away from everything else carefully. So we're not going to look at these things that are necessarily bad. In fact, I can show that things like this almost invariably define the integers anyway, right off the bat. So, oh, as an interesting side note, however, take one of these guys. Okay. Now, sure, okay, it's dense and codense. It's this wacky thing. What happens when you add that to the field of reals? Well, not much, as it turns out, although it's very difficult. It's very tedious and long-winded to prove, and I don't know that anyone's done it. What happens then is that you don't get any no new open sets, no new constructible sets. You sort of blur your eyes. If you blur your eyes looking at this thing, all you wind up seeing is this. And this is essentially what happens with all the definable sets in some language that we might have heard. I don't know, that the open core is just the field of reals. There's no new open sets. So these guys, you can throw them on top of the field of reals. But they can't really be seen. They can't be seen by the field structure. They're hiding in there too slyly. I guess we might get around to asking Philip at some point what the status of this thing is, of the result itself. I shouldn't say too much more than that. These guys, on the other hand, they can be spotted. They're definitely spotted by the field. And in fact, you define the integers in general. So we could talk a little bit more about that later, but definitely bad. Okay, good in one sense, but not in the one we're interested in, because we're not expanding. Now we're looking at a trajectory that's not constructible or regular or whatever. So we'll be ruling out ergodic behavior, if you will, and also fractal behavior.
Chris?
Yes.
Yes, sorry, just to be sure I got it. Are these examples of trajectories that are not locally trajectories of the function?
Yes. Yeah. In both cases, they are not. They don't have that property. No matter how small you look, you're going to wind up. No matter how small you look and look at an intersection, you're going to wind up getting infinitely many components of the original trajectory. Yeah. So these are bad. These are bad.
Okay, thank you.
Okay, as long as we've gone this far, let me just remind us. Well, I'll remind us all of this, and then maybe I'll have to quit a little early today, and we'll see how that goes. Voice is running out. So as I said, these guys here can be seen and are detectable as bad, as defining the integers. So where does that come from? This comes from some other recent work of Philip and I. And I'll just, because this one, nobody gets this, I don't think anybody gets this definition seen once and then it's in your head. So if we start with an arbitrary metric space and a set in there, and we take a positive radius here. So we let this thing be the number of balls of radius r needed to cover r, Again, I'm letting that be infinity just for ease. All right, now the Asawa dimension of E. is this monstrous thing here. So it's the inf of all the s's. The s disappears until right the very end here. But it's the inf of all of these things for which there is a global constant relative to E. So this is for all x and E. And you think of this as a scale for all little r and big R bigger than 0 with this relationship, that this number, you look at the ball centered at the point of the bigger radius, you intersect that with E, and then you look at this covering number that we need here, that it's controlled by the ratio here and this constant in S. Yes, and again, it takes a bit of getting used to. This is something that comes up in an analysis on arbitrary metric spaces. And the motto that I learned from some of the experts there is that it measures the size of E in all scales and essentially at all points as well, right? No matter where I look, this basically really is saying, another way to think about this is that how does this wind up getting big? The number of things needed to cover E. Say, if it happened to be a say if it happened to be a trajectory, for example. You might need more if it's curling a lot, right? If it's zigging back and forth a lot, your object of interest. And then as you look at finer and finer scales, you look at smaller radii, then you're going to need more and more and more balls to cover up the winding. If this sounds at all familiar, this is related to so-called Minkowski dimension, or some other French name I can't remember right at the moment. So this has to do with how much wobbling you can do, but it's global control of everything, right? No matter where you are, no matter what scale you choose, you have a control on the number of balls that you need to cover these things. Okay, so there's not much, that's what it's about. And why do we care about it? Well, there's a couple of reasons why I care about it. It's for one thing, all of the things called dimensions, all things that are properly metric dimensions. In other words, if you have a dimension function that's just defined for arbitrary metric spaces, nothing special about the metric space itself. Such things that you run across in the literature are all bounded below by topological dimension. And of course, there's three possibilities there, but that's all right. Certainly of the smaller ones, the small inductive dimension. And they're all bounded above by this. Now, this is just an observation. It's a heuristic. It's not a... I started asking people, do you know of any, is it possible to construct a metric dimension that would be bigger than this? And some people at first said, oh, sure, no problem. And then realized that, well, no, you actually can't get all of the, if you write down what you mean by metric dimension, if you really want it to have the certain properties that you want, no one's found a bigger one yet than this one that I know of. So that's pretty cool right there. It seems to be a cap on dimension theory in geometric measure theory, fractal geometry, and analysis on metric spaces. Okay, So this is why one of the reasons why I fell in love with it immediately. The Asawa dimension of the integers is 1. So there you have it. You have a uniformly discrete subset of your metric space, in this case R. Nevertheless, it has the same dimension as the ambient space. So there's some sort of arithmetic, there's some content here that goes beyond the usual kind of stuff that one runs across. So for example, one of the things I don't like about Hausdorff measure or Hausdorff dimension, Hausdorff measure in particular, is that, well, all countable sets have Hausdorff measure 0. So, well, no countable sets can matter. No, we know that's different as logicians. It's simply not true that all countable sets are equally troublesome or equally non-troublesome. So this really made me fall in love with the whole notion, and I started looking into this seriously. So here's what I had already said earlier, that all the dimensions on Rn and commonly encountered in geometric measure theory, fractal geometry, they're bounded below by topological dimension and above by dim. So I think these, taken together, these are definitely good reasons to be looking at these things. And the reason why I'm bringing up now is it's a very special case of Philip and I. What we can say is the following. If you take a finite union of regular trajectories of any vector fields, doesn't matter what, no assumptions whatsoever. And so you expand the field of reals by this finite union of trajectories. If you don't get the integers, if you stay in the worlds of possibilities for us, then you have to have Asawa dimension 1, which is the naive dimension of a regular trajectory in the topological sense. So you can't have much wobbling. You can't have any kind of fractal behavior. You can't have any of this. It's known here that these guys, for example, it's known that they have positive Hausdorff dimension or something like this, or packing dimensions or whatever. It's known that they're bigger than 1 is what I should be saying here. So these guys, by our result, automatically define the integers. And so there's another good reason to throw them out, not just because we don't like them because they're unpredictable, but also because we'll necessarily have to throw them out if we're not going to define the integers. So, but as I said, this result at the moment uses only that, I'm not really using much of anything about trajectories here or vector fields or the special structure that they might have. At the moment, I'm only using that, well, we've already said it doesn't define Z, okay? And it has topological dimension 1, and it's a Boolean combination of closed sets. It's constructible. So I think what's, one of the things that I'm still missing from this program is what else can we say about dim1 Asawa dimension 1 trajectories of definable vector fields if the contention holds for R. So this is a big mystery to me still. It seems like, trajectories, maximal trajectories of things automatically come with a group structure, right? It's that, well, if I go for a while and then if I go for t units of time and then I go for s units of time, I went for t plus s units of time. So trajectories are special things in that respect, but I haven't yet figured out what to do with this, what, if anything, to do with this fact in this whole enterprise of what I'm calling tame control theory, which again maybe should be called tameness theory and control theory or something like that, but we'll stick with it for that. So what I hope I've done at this point is made a reasonable case for this contention of mine that we really should be playing this game only over O minimal, field of exponents Q, and we have to have the compact linear trajectories around in order to avoid who knows what kind of open problems in analytic number theory. I hope I've managed to convince you that this is worthy of looking at, and that there are also some big mysteries going on here that might or might not pan out to be something very cool. I think there's a lot of research that can be done here, hint, hint, grad students. And so when we reconvene, the lectures after this are going to get more technical and more vector field theoretic and ODE theoretic to start looking at what happens in these things as opposed. But I really, really think it's important to understand why we should look at them. There are good reasons to look at them. And I think it's a fascinating interplay of using, technical methods of first order logic to, well, let's just say that some of my buddies in the philosophy department are more interested in, they're very interested in this idea of trying to justify intuitions of professional mathematicians by actual arguments, by actual proofs and things. So I think there's a lot of fun stuff here, and I hope other people will have fun with it too. And I think with that, I will stop because my voice is about to go.
Okay, thank you, Chris. Let me stop the recording.